Alright, today we're going to talk about refraction. Refraction occurs whenever a wave passes from one medium into another. The densities of these mediums are going to be different. Typically, each medium has its own density. So whenever it passes from one medium of some density into a different medium with a different density, the actual path that the light is traveling is altered. And so we often describe it as the light is being bent. So when we say that the light is bent, you need to understand what that means. The path along which the light is traveling is supposed to be a straight line. We have said multiple times light travels in a straight line. But when we have a situation where the light is going to pass from one material into another, and the second material is of a different density, then instead of the light traveling along the same path, that light is going to experience some sort of change in its path. And so if we say, well, this was the direction it should be going, but here's the direction that it's moving instead, then we describe that as being bent. Okay, the path in which it is traveling has been altered. So if we look at some of the images on this slide, we see over here on the far left-hand side that we have a light that is coming in, or some sort of wave, and it enters into whatever that dark blue substance is. So it's in one environment, whatever our white background is supposed to be, and then it enters into a different environment, a different material or medium, whenever it enters that blue section. So the light is going to bend, or that path is going to be altered when it enters that second material. And then in this particular example, it bends again because it moves out of that material into the original medium. So that light is actually going to bend twice in that example. Let's look at the picture of the pencil in the cup of water. You may have noticed something like this with a straw inside of your glass, maybe when you're out at a restaurant. It may look like the straw is not in a straight line, but we know that the straw is straight. This is not one of those silly straws, it's a regular straw. This is not some sort of weird pencil, it's a regular pencil. What happens in this situation is the light is traveling in two different materials. So the way that we see the light is going to be different when we see the light passing through air compared to the light as it passes through the water. So if my pencil stays in the air, then here is roughly where my pencil would be if my pencil were not in the cup, but it was just being held out in the air. But since it goes from the medium of the air into the medium of the water, that change in medium brings with it a change in density. And since it is of a different density, that is going to affect the speed with which the light travels through the new medium. So we'll get into the details of how exactly the speed is altered in a moment, but simply understanding that it's moving at a different speed, that's what causes it to follow a different path. So in this situation, instead of the light traveling in a straight line like it should in the air, that light is bent. And so now the light is going to travel so that it has shifted over, right? And so that's why it looks like our pencil is broken or it is bent. It's not really bent. It's a regular pencil. It's just that it has passed into a new medium, and that medium has a different value for its density. that corresponding density has changed the speed with which the light is traveling through that medium. If you recall from our waves chapter, we just kind of said in general the speed with which a wave travels depends upon the medium that it's in. Well, it went into a new medium. It has a different speed and in that different medium. And so that's what causes the light to quote unquote bend. The image at the bottom of the slide of the boy who is trying to spear a fish, he's going to miss most likely unless he's very experienced and knows how to adjust his aim, because you can see from the illustration the light that reaches his eye is what they have drawn with the alternating red-orange line. That is showing the path that the light appears to be coming from. So kind of like the lesson with our ray diagrams where we talk about that virtual beam of light where it appears to our brain as though the light originated from this location. It's exactly what's happening here. It appears to the man that the light is following this red path, but we can see that in reality, the fish originated from the orange path. The light coming from the fish is traveling at a different speed when that light moves through the water compared to when it reaches the air. The air is of a different density, therefore the speed of the light changes, which alters the path that it's moving. So the man most likely is going to aim the wrong location and is going to miss the fish. The picture of the man holding his glasses I just found kind of comical. This is a lens that is curved, and we're going to get into more detail in that in our lens lesson. But the light is going to bend, number one, because it's entering a different medium, so the wave speed is going to change. But in this particular case, the lens is also curved. So the fact that it is a curved lens is going to also cause the path of the light to change. And in this case, it shrinks down the image, and that's why the man's eyes look tiny in the lenses, which is rather comical on his regular size face. The image to the right of a vision test, you can see in the background that the letters are all blurry. If you've ever been to the eye doctor, they put the little lens set over your face and then they switch lens 1, lens 2. Is it better here or here? And what if I do this? And all they're doing is they are putting the light through different amounts of refraction that is adjusting the image, and it's adjusting how you perceive that light to be, because when it passes through that lens, the path is altered, which changes how the light hits your eye, which changes the image that is created. So refraction can do some really cool things. On this slide, you may notice that there's a few different blue arrows. If you pull up the PowerPoint on Canvas, you will find a linked PowerPoint on my Canvas that has hyperlinks for these different images. So everywhere you see the little blue arrow, there's a video attached to the PowerPoint. So there's some really neat videos out there. If you just go to YouTube and type in refraction, there's lots of cool things that we can do with refraction. So let's start off with the prism. Refraction causes the speed of a wave to change because it passes into a new medium. So we have a couple of different things happening in this first picture. The first thing I want to focus on is refraction, because that is our topic today. So the light is traveling along this path, and if the light does not change mediums, it's going to follow that green line. But the light does not stay in the air. It enters this prism. The prism is made of a different material, and it has a different density. So as the light enters the prism, it is going to change speed. It's either going to speed up or it's going to slow down. In this case, it's going to slow down, and I'm going to explain how you know what it does in just a moment. But because the speed has changed, in this case specifically, because the speed has decreased, because it's not moving as fast, it's not going to travel as far. Now, that's a relative term. It's not a technical term. But if this were a race, if we were running and we were saying how far away did our light travel, well, it's moving slower now. So it's not going to travel as far. I'm drawing over a rainbow, so that might be kind of hard to see my orange line. But this is the path that the light traveled. So we would say that it moved slower. And so the path was bent along this orange line. When the light exits the prism and then goes back into the air, our medium once again is the air, then the light is going to change speeds again. And so it is now going to follow this path. So you can see, compare where the light was supposed to go originally to where it ended up. Yes, that is a very different path. So the first thing I want you to recognize is that this is demonstrating refraction, changing the path, or quote unquote bending the light, because new material, new density, different speed. The second thing that we have happening in this example is something called dispersion. And you can see that the word dispersion is defined here as separation of light, or separating light into its different wavelengths. Now, we've already learned about light, and we should understand that white light contains all the different colors of the rainbow. So when the light is refracted through the prism, it's going to change the speed that the light is traveling. And if you recall, white light is made of all the different colors of light, and each light, or each color, has its own frequency and wavelength. So since we have multiple waves within that white light, as kind of a side effect, a secondary effect of the refraction, we get the different colors spread out because they are all affected differently by the refraction. And so we end up seeing the different colors of the rainbow. The image below that of the rainbow in the sky is explaining to you how the light is going to be refracted through the air molecules in the sky, which is going to cause dispersion, which spreads the light out into its different colors, and that's how we see rainbows in the sky. So I have 3 different videos linked here. The top video of the prism is explaining in very good detail how the path is affected because the speed changes through your different mediums. The bottom image of the rainbow explains mostly the idea of the dispersion, where we have white light that is spread into its different wavelengths. Into the different colors because of the different wavelengths that correspond to the different colors of the rainbow. The middle link next to the word dispersion actually describes both. It explains both the refraction and the dispersion, and it does a little recap of at the end of the main ideas and vocabulary. So I would recommend that you actually watch all 3 of them so that you get a good understanding of what happens to our light. The video on the right says invisibility. So this has the little blue arrow or blue triangle, which means that this is a linked-in video through the PowerPoint. This is pretty cool. I just find this fascinating and interesting, and it is refraction. So they're showing you how you can make a test tube disappear. If you've seen the movie Predator, they reference that. I know I talked about that in class the other day as well. The Arnold Schwarzenegger version, the original Predator, is what comes to my mind and what they reference in this video also, but give it a look. It's just pretty cool. So showing you how refraction can make it seem as though something has disappeared. Down at the bottom right, I have a picture of another example of refraction. And so in this image, I want you to see that it looks like we have blue light coming from the road. Now, a little bit of background information. This would be a situation that we here in Texas might experience in the middle of the summer. Have you ever driven on the highway or some road in summer? So for us, this would be July, August, when it's super hot outside, and it looks like there's water reflecting off of the road. But you say, wait a minute, in July in Texas, we don't get rain. So that can't possibly be water on the highway. What in the world am I looking at? Why does it look like there's water on the road? Well, this is what we call a mirage. A mirage is a special type of optical illusion. Your mind is being tricked into thinking that it's seeing water on the ground, but it's not. What you're seeing is the blue light from the sky being refracted through the air just above the surface of the ground. Because of the temperature change, it changes the density of the molecules of the air at the surface, and that is going to cause the light to refract at such an extreme angle that it actually comes back up towards your eye. So you are seeing refracted light from the sky that is now coming up at your eyes. Now, I've commented before that our brains are amazing. It does awesome things, processes information super quickly, but it also remembers past experiences. So we assume, at least initially, that there's water on the ground, because typically when we see blue light coming from the ground, it's water. But in this case, it's not water. It is refracted light from the sky. So that's just a pretty cool little thing that I wanted to talk about. All right, so now let's talk about how are we supposed to know what the wave speed is, or how the speed is going to change because of the new material. So there's lots of images going on. Let's focus, for starters, on the top left picture. Here we have an illustration of air and water. You can see that they are labeled medium 1 and medium 2. We have our incident ray. So remember, incident is the original beam, and it is going to strike this boundary. So it's going to hit the top of the water. Now, some of that light is going to be reflected, and we're not going to focus on that right now. We're going to focus on the light that passes through the boundary. So the light that passes through the boundary is going to now enter into a new medium. And you probably already knew that water is more dense than air. The molecules in water are more compact than they are in the molecules of the air. So this means that it has entered a substance with a different density than what it was originally traveling in. So it is going to change the speed. Now, how is that speed going to change? How are we supposed to know how the path changes? Well, we are going to understand that the original path of the light should have been here with my highlighted green line. But the actual path of light doesn't follow that line. Now, we have our normal line, so let's review. The normal line is always perpendicular to the boundary or our surface. So here is our normal line. We are going to measure our angles from the normal line. So we can see that the path that the light was supposed to travel here and the path that the light actually traveled here are not the same. So how was that path adjusted? Well, the line of the motion has moved so that it is now closer to the normal line than where it should have been. So we say that the light has bent towards the normal line. This is supposed to have the symbol theta for our angle. I guess it got lost in the transfer. So our angle theta is going to be smaller if our light is traveling slower through that medium. If this were a race and we started from the normal line, because this is our reference point, here is how far from the normal line our light actually traveled because of the refraction. But if it did not travel into the water, but it stayed in the air, this is how far from the normal line it should have traveled. So indeed, it was not moving as fast because it did not go as far away from the normal line. That's one way to approach this. Now, it's technically not the right way to decide what that angle is, but just kind of conceptually to give you some sort of analogy to help this make sense. What we do want to correctly recognize is that the angle of that refracted light, so let's find something that's going to show up. The angle is measured from the normal line to the refracted line, and so there is my angle theta for the refraction. The angle of incidence is also measured from the normal line. And so if we compare these two angles, the refracted angle is indeed smaller than the original incidence angle. And so that's going to indicate that my wave moves slower in this second medium, in this case, water. Now we have a formula over here to the right. N equals C over V. What does that mean? Well, not only can we interpret how the speed is going to be affected, we can actually perform some calculations. If we know the medium, then we can take that known medium and use its information to calculate what the wave speed is. If we know how the speed of the wave has been affected, so if we know what the speed of light is supposed to be, which we do, that's the value C that we learned about, which is our speed for all electromagnetic waves. This is how fast our light would be traveling if it were moving through a vacuum or outer space where there are no particles to interfere with its motion. So if we have our light moving through space or a vacuum, it would travel at 3 times 10 to the 8th meters per second. So that's our C that we find in the numerator of this equation. If we know the actual speed of light because it went slower in the water, so it's not moving 3 times 10 to the 8th meters per second, it's moving some value less than that. So maybe it's 2.7 times 10 to the 8th meters per second. That would be slower. That goes in the denominator. So we are going to get a ratio. We like the ratios in this chapter. Of the speed of light, 3 times 10 to the 8th meters per second, divided by the actual speed in water, which I'm just making up, 2.7 times 10 to the 8th meters per second. So when we perform that calculation, our units are going to cancel. This is a ratio, so it's going to give me a value without a unit that's going to show how those two speeds compare. So our N value is not going to have a unit because our units will cancel. But this N value does have very important meaning. It's going to give me an indication as to whether my new substance, or the substance that I'm calculating it for, is more dense or less dense. So a value of 1 means that the speed of the wave is equal to the speed of light. So this would be an environment where the speed did not change. That's going to take place in a vacuum, in outer space, and actually through air. The density of air is so small that it actually does not affect the speed of light. So when we're in the classroom and there's light shining from the light bulb down onto your page, it's traveling at the speed of light, 3 times 10 to the 8th meters per second. So air has an n value of 1. But if it's traveling in some other substance that is more dense, like water, the light is not going to travel at 3 times 10 to the 8th meters per second. In water, it's going to be slower. So we're going to get an n value greater than 1 because our c value is greater than the actual speed. So we're never going to get a decimal answer. If you get a decimal for your n value, you messed up somewhere. We can never travel faster than the speed of light, okay? But that n value is going to be a smaller value, so close to 1, for substances that are not very dense, which means the speed is not adjusted very much. The more dense our material, the bigger the n value, which means that there's going to be a greater change in the speed and my object is going to move even slower. So it says under the picture on the right, the greater the index of refraction n, the slower the speed of the wave, which would be the variable v, through that medium. So in this illustration, they provided you with some n values. Here they told us air has an n value of 1. In this situation, we have sunlight that is passing through the air and then shining into a piece of glass, perhaps a window. And they give us the n value of the glass. So from this n value, I can see that glass is more dense than air because it has a larger number for n value. I can see or interpret from that information that the speed of the wave is going to decrease as the wave moves into the glass. I can see that from the illustration because this angle, theta, for my refracted light is going to be smaller than this angle, theta, for my incidence. And we are going to choose to use the numbers 1 and 2 to identify these two angles. My angle of incidence could be identified as theta I, that's what they call it here in the picture. And my refracted angle could be identified as theta R for refraction, but we're often going to just say the first medium and the second medium. So I can see that my theta 2 or my refracted angle is smaller than the incident, so that, based off of what we were told over here, tells me that the speed is slower. I can also look at the picture and go back to understanding that this is the path that the light was traveling. So if it did not change mediums, it should have ended up over here. And the fact that it moved towards the normal line to follow the actual path tells me that it was moving slower through that second medium. Okay, so here we have another equation, and this is called Snell's law. And this says n1 sine theta 1 is the same as or equal to n2 sine theta 2. So what in the world does that mean? This is a relationship. N1, the n value, is this ratio number that corresponds to the different types of materials, and it has the same trend as the density of that material. So bigger n values are more dense, smaller n values are less dense. Bigger n values, the wave is going to move slower. Smaller n values, the wave will move faster. So n1 sine theta 1 says that we're going to take the n value for the first material, the first medium, and we are going to multiply that times the sine function of whatever that incident ray was, so theta 1. That is equal to the n value for the second medium. So as you are interpreting your word problems, you're going to need to keep track with what material it started in and what material it finished in. The second medium is going to be N2, and we're going to multiply that by the sine function of theta 2, which would be the refracted angle. We have some values here on the screen for your practice work. You're also going to be provided a little chart that gives you some n values. There are going to be some that you are expected to know, like the n value for air or a vacuum is 1. Again, that just means that the speed of the wave is the same as the expected speed of light through a vacuum or through outer space. We're going to use water quite a bit, so you may learn that one. But for the most part, we will give you either a chart or simply state in the word problem what those n values are, so you have them to plug into your formula. Later, I will do a couple of practice problems so that we understand how to actually plug numbers in and manipulate this equation to do some calculations. But for right now, I just want you to understand that we are simply creating a relationship showing how our light is moving through the first substance and how that relates to the light moving through the second substance. From this formula, I can calculate what the n value is for either of my materials. Let's say that we have light that is traveling from air into water, and what if I didn't already know what the n value for water was? If I knew the angle, and again that's measured from the normal line, if I knew the angle of incidence and I knew the angle of refraction, then I could determine what the n value for my water is by simply plugging in the other values. Remember, you're supposed to know air has an n value of 1. If I maybe knew what the n value of my second material was, so let's say the n value was known, and I wanted to figure out what angle will that light be refracted, then I would plug in theta 1, N1, which is air, so it's the number 1, and then N2 in this case would be water, so 1.33. So I could simply plug in these numbers and then do my algebra to solve for the angle that the light would then be refracted. Okay, so that's how that works. And we'll work some practice problems later. Okay, so the light is going to be refracted. It is going to bend. As I change my angle of incidence, that is going to change the refracted angle. So if instead of the light coming in at this angle illustrated here, if my light came in at a different angle, then the way that the light is refracted is going to change. It is going to change its path from what it should have been to something different. If it moves into a more dense material, it's going to have a slower speed. So it's going to bend towards the normal. And as we continue to change that incident angle, it's going to refract, and eventually we're going to have our light bend so that it's going to run parallel. So this incident light is going to actually run parallel to the surface. So if we continue to increase our angle, instead of refracting through the water, instead what we're going to get is a light that reflects out of the water. So this threshold, this turning point, if you will, that determines whether the light is going to be refracted or reflected is known as the critical angle. And so we have a formula here, sine theta, and we put a subscript of C for critical. is equal to, and look at that, another ratio. It's just the relationship between your two n values. How dense is my second medium, or what is the n value? It's not a density. Don't get confused. I apologize. The n value is not a density. Density is a different calculation. There's just a correlation here. So a lot of times in my description, if we can comprehend that this is related to the density, then a lot of times conceptually it makes it easier for us to understand what's happening or maybe make predictions about what's happening. So the n value of our second substance, so in this case the water, divided by the n value of our first substance, in this case the air. So that ratio is going to be used to give us that critical angle. You see here on the screen that we have another one of those little blue triangles. There is another link to a video where they are describing refraction. I want you to also understand that the light does not always originate from the water. If I had, and in the video they will put a scuba diver in the water, if I have my light originating from the water, then this would be my N1. So the light would be shining out, right? So this is the path that it would follow. So if the light is not bent, then it would follow this path. And so my air would be in 2 in this case. So this is the light path, the path that the light would follow if it stayed in the water. But you can see from the drawing that when it passes into the air, it actually experiences a greater angle than what it would have experienced in the water. What does that tell me? That tells me that the light increased in speed when it moved from the water into the air. That makes sense. Water has a larger n value than air, so larger n values, the speed is slower. So as the light moves from the water into the air, a slower n value means that the light's going to move faster. So it's going to bend away from the normal line. We are going to have a greater angle. So make sure that you understand that it doesn't always have to go down from the air into the water. It just needs to change from one medium into another. All right, down here I have something special that takes place. If we can find that angle where the light, instead of refracting so that it passes out, if we can find that angle where the light is then reflected, we can create something called total internal reflection. And so this is something that's used in things like fiber optic cables, where they are trying to get that signal to pass through the cable as fast as possible. So the speed of light is about as fast as we're going to be able to transfer information. So in fiber optic cables, they actually use the idea of reflection to cause the light to reflect inside of the cable, and then the light basically gets trapped, it gets stuck. Remember, light is a wave and a particle, so it can send that information through our light along the tube using total internal reflection. All of that light or energy is trapped and gets passed along at the speed of light, so super, super fast.